Marhaba. Okay, in this video, we want to reinforce or support, strengthen our stock of rules of inference with another 4 new rules. And these new rules will take care of statements which include quantifiers. Remember, check that all the previous rules of inference were talking about statements with no quantifiers. So let's see, we have 4 new rules. The first one is called universal instantiation. What does it say? That the following is a valid argument. What is the following? It has one premise. So suppose for all x in your domain p of x is true, and suppose c is a particular element in your domain. Then you can conclude that c has property p, that p of c is true. Again, if every element in your domain has property p, which means for all x p of x is true, then this particular element c has property p, which means p of c is true. Okay, so here you imagine a universe and one of the elements in the universe is called c. Now, this is a valid argument. Why? Because if the premise is true, then the conclusion is also true. What is the premise? The premise says that every element in the domain has property p. Now c is one of those elements, so it has a property. It has the property p, which means we can conclude that p of c is true. So this says universal instantiation. Let's go to universal generalization. It says, suppose property p holds for any arbitrary element a in the domain. So suppose you choose randomly any element in the domain and you find out that, so you choose an arbitrary element and you find out that this element has property p. And whenever you choose any arbitrary element, the element has property p. Suppose this is true, so this is the premise of the argument, then we can conclude that the conclusion is also true. What is the conclusion? That every element has property p for all x p of x. Okay, let me say a few words here. What do we mean by arbitrary? We mean that the element a, all what we know about is that it belongs to the domain. That's it. Okay, so that it comes from the domain and it's not a specific one. It could be any element in the domain. So all what we assume about the properties of a, that it belongs to the domain. So for example, if the domain is the set of integers, then, and I want to show that a property holds for all the integers, then this element a should be chosen to be just an integer, no more. You shouldn't assume that a is even or odd or prime or 7 or a multiple of 3. You shouldn't assume, we don't assume any property about a except that it comes from the domain. So if you choose arbitrary element in the domain and you find out it has property p, then every element in the domain has property p. So for all x p of x is true. This is universal generalization. Again, what is universal generalization? If any arbitrary element a in the domain has property p, then every element in the domain has property p. Okay, let's look at the existential quantifier, existential instantiation. Suppose this is true, the premise is true. It says there exists x in the domain such that p of x. So what do we know if this is true? We defined this proposition to be true if there is at least one element in our domain with property p. Now, so we know this element exists in the domain. Maybe we don't know which one in particular, but we know there is one. So all what we know that such an element exists, and let's say we call it c. Once we call it c, then we know that c has property p. Okay, so again, existential instantiation rule says if there exists x p of x is true, it follows that p of c is true for some c in the domain. So for some c in the domain, it has property p. Okay, I hope you see why it's valid, because there exists x p of x. Again, this is an argument. It has one premise and one conclusion. if the premise is true, if there is an element in the domain which has property P, then P of C is true for some element C in the domain. Okay, some element called C has property P. Existential generalization. Suppose you know a particular element in the domain C with the property P. Okay, suppose you know this. So you look at the domain, you found an element C, and C has property P. Then you can deduce that there exists X, P of X is true. Okay, why is this? Why this is valid? Suppose C has property P, then why this element is this proposition is true? What does it say? It says there exists an X in the domain such that P of X is true, such that X has property P. Okay, this is true because we know a particular element. We assume that we know a particular element C which has the property P. Okay, so these are the four rules, new rules: universal instantiation, universal generalization, existential instantiation, and existential generalization. We want to use these new rules together with the previous ones to prove the validity of this argument. Okay, what is this argument? It has two premises and one conclusion. The first premise says a student in the class has not read the book. Premise 2 says everyone in the class passed the exam. We must conclude that if statement 1 is true, which means if there is a student in the class which has not read the book and everyone in the class passed the exam, it must be true that someone who passed the exam has not read the book. Okay, so we want to write a formal proof showing the validity of this argument. Remember, what is a formal proof? It's a statement of sequences where each statement is either a premise or deduced from previous ones by rules of inference or logically equivalent to previous one or a tautology. Okay, so let's see. Now, the first step to show that this argument is valid is to translate it into predicate logic. So I want to use some predicates to translate these sentences. So I want to use the following predicates. We will use three predicates. C of X, which says that X is in the class. So this is C of X. It says a predicate is a statement talking about variables. So C of X says X is in the class. R of X says X has read the book. P of X says that X has passed the exam. And the domain of the variable X is all university students. So here we have the university students and we have the students in the class we are considering. Now let's use the predicates C of X, R of X, P of X together with their domain, all university students, to translate this argument. Okay. So how do you translate the first one? A student in the class has not read the book. So a student in the class means there is some student in the class. So I want to say there exists an X in the domain. But what is our domain? It's all university students. So until now, I wrote there is some university student. But what do I want to say about it? That it is in the class. Okay, I want to say that this student is in the class we are considering and did not read the book. So there is an X, there is a university student such that this X is in the class. So C of X, X is in the class, and did not read the book. So read the book is R of X, so not R of X. This is the first premise. The second premise says everyone in the class passed the exam. So here, clearly it's a universal quantifier for all X. But until now, for all X in the university, so every university student. But the statement says everyone in the class passed the exam. So I want to say for all X, for any university student, if this university student is in the class, so if C of X, then it passed the exam, P of X. So look what we are saying here. For any university student, if this student is in the class, then it passed the exam. Okay, this is the translation of this statement. Everyone in the class passed the exam. Now, what is the conclusion? The conclusion says someone who passed the exam has not read the book. So there is some student with two properties: passed the exam, so P of X, and has not read the book, so not R of X. Okay, our goal now, so now we have done the translation to predicate logic. So see how we are using logic to express statements. Now we want to use the rules of inference to start with the premises and arrive to the conclusion. Let's do this in a formal proof. So remember, in a formal proof, we write a sequence of statements. So let me just zoom in. Okay, so let me start with the first premise, which says there exists a student who is in this class and did not read the book. This is the first one. The second one, and what is the justification of assuming this is to be true? It's a premise. The second one is that for every student in the university, if this student is in the class, then it passed the exam. And this is the second premise. Now we need to use the rules of inference, any rule of inference, to keep doing deductions until we arrive to our desired conclusion, which says there exists an X, someone who passed the exam and has not read the book, and not R of X. So this is our goal. Okay, we need to arrive to this statement using rules of inference, assuming the premises to be true. So let's see, what is the first step here? Is existential instantiation. So we know there is, this statement is true, there exists an X with this property. So we know some element in the domain in the university has this property. Let me highlight it. So we know this element exists. Let's call it A. Okay, so this is existential instantiation applied to 1. So there is some student A, we don't know which student, but let's call it A, with the property that, with the highlighted property that it is in the class, so C of A, and has not read the book, and not R of A. So here you imagine this is the university, and this is the class we are talking about. There is a student A who is in the class and did not read the book. Okay. Next, okay, look at the second one. It says every university student has this property. C of X implies P of X. But A is one of these students. It is in the universe. So it has this property. So this particular student has the property that, okay, let me highlight it first in blue. It is this property. So this student has the property that C of A implies P of A. So what is the property? If A is in the class, then A passed the exam. Okay. Now 5. Look, I have a conditional statement. Let me just fix this C. I have a conditional statement with this hypothesis, C of A. Can I get it from here? So, sorry, this is a universal instantiation. Instantiation applied to 2. Okay, so let's check what is universal instantiation. It says if some universal statement is true and C is a particular element, then the property P is true for the particular element. So we know that this property, the highlighted in blue, is true for all elements in the domain. A is a particular element, so it's true for this element. Okay, now let's use simplification to 3. So the simplification rule to 3. So now look, C of A is a proposition and not R of A is a proposition. So I have, say, P and Q is true. By simplification, P is true. So this, we conclude that C of A is true. Now statement 6, look, this is the formal proof. Okay, see, this is the formal, we are writing a sequence of statements where each one of them is a premise or deduced by a rule of inference. Okay, now we can apply modus ponens to 4 and 5. Why is this? Okay, how is this? This is a conditional statement with a true hypothesis, then the conclusion is true. So its conclusion P of A is true. Okay, now, so now we know that A has passed the exam at this point. Now we can apply simplification again, or if you want to be more precise, I can use that this statement 3 is logically equivalent to not R of A and C of A. This is a logical equivalence. Remember which one? That P and Q is logically equivalent to Q and P. This is commutativity of conjunction. So this is C of A and not R of A is logically equivalent to not R of A and C of A. This is 7. Say 8. What can I do with 8? I can do simplification again. This is a conjunction, it's true. Then the first one must be true. This is by simplification applied to 7. Okay, now look, what do we have now? We have this one, number 6 and number 8. P of A is true and not R of A is true, then their conjunction is true. So P of A and not R of A is true. What is this? This is conjunction rule. The conjunction rule applied to 6 and 8. Okay, remember the conjunction rule says if P is true and Q is true, then we can conclude that P and Q is true. So if this one is true and this one is true, then their conjunction is true. And finally, we can apply existential generalization. Existential generalization to 9. Okay, if you know that some element in the domain has this property, then the following statement is true, that there exists an X in the domain with this property, P of X and not R of X. Okay, and I think this is the conclusion of the original argument. There is an X who passed the exam and did not read the book. Okay, there exists an X, P of X and not R of X. So to show, again, moral of the story, if we showed that this this argument is valid. What is this argument? It has 2 premises and 1 conclusion. And whenever the 2 premises are true, the conclusion must be true. Which means if you have a class which has a student that did not read the book, and you know that every student in your class passed the exam, then you conclude, you know that some student who passed the exam did not read the book. And what is the proof of the validity? It's this sequence of statements. And look that this sequence uses the 2 premises and uses rules of inference. See, until we arrive to the desired conclusion. Okay. Let's stop here.